Aldehydes and ketones share one weakness, the carbon right next to the carbonyl, the alpha carbon. Its hydrogens are slightly acidic, because removing one gives a resonance-stabilized enolate, or, in acid, the neutral enol. This single idea, enolization, explains three things at once. How these carbonyls are halogenated, how their alpha hydrogens exchange, and how Stork's enamines let us build new bonds at the alpha carbon. In acid, halogenation begins with the slow step, enolization. The carbonyl oxygen is protonated, an alpha hydrogen leaves, and the enol forms. The enol is electron-rich at the alpha carbon. It attacks the halogen molecule, and after losing a proton we get the alpha halocarbonyl. The rate depends on the ketone and the acid, but not on the halogen, nor even on which halogen it is. That proves enolization is the rate-determining step. In acid, the reaction usually stops cleanly at one halogen. In base, the slow step is forming the enolate. Hydroxide removes an alpha proton, giving a resonance-stabilized enolate. The enolate attacks the halogen. But now each halogen already added makes the remaining alpha hydrogens more acidic, so the reaction speeds up and is hard to stop. That runaway halogenation is exactly what drives the haloform reaction on methyl ketones. Acid gives one halogen, base tends to give many. The same enol or enolate explains alpha hydrogen exchange. In heavy water, every alpha hydrogen is quietly swapped for deuterium, through the very same intermediate. And here is the beautiful proof. For a given ketone, the rate of halogenation, the rate of hydrogen exchange, and the rate of racemization are all equal, because all three funnel through one rate-determining enolization. Gilbert Stork found a gentler way to use the alpha carbon. Treat the ketone with a secondary amine, such as pyrrolidine. The amine adds to the carbonyl, water is lost to form an iminium ion, and an alpha proton leaves to give an enamine, a carbon-carbon double bond joined to nitrogen. Like an enol, the enamine is nucleophilic at the alpha carbon. But it is neutral and easy to handle, with no strong base required. The enamine's alpha carbon attacks an electrophile, an alkyl halide or an acyl chloride, forming a new carbon-carbon bond and an iminium salt. Simple hydrolysis then releases the product, the alpha-substituted ketone, while the amine is regenerated. The payoff is control. Stork's enamine gives clean monoalkylation at the alpha carbon, avoiding the overreaction and side reactions of direct enolate alkylation. One idea ties it all together. The alpha carbon becomes nucleophilic through an enol, an enolate, or an enamine. Halogenation, hydrogen exchange, and the Stork reaction are all that chemistry in action. Control the enol, and you control the alpha carbon. The carbonyl, decoded.